VB side, and so they can interact very frequently because they are trapped. And also the light emitted is trapped within this layer because the refractive index of gallium arsenide is more than the is quite larger than the refractive index of gallium aluminium arsenide. So these facts are made use of in the construction of the quantum well lasers. And now I will show you the construction. You can just move downwards, just scroll down slightly, and here scroll down slightly. Here you can see the uh, the the kind of structure that I was referring to. There is p-type gallium aluminium arsenide on one side, and there is n-type aluminium gallium arsenide on the other side, and in between these is a layer of gallium arsenide, and that is the one that constitutes the quantum well. So as they say, the quantum well laser is an improved version of the ordinary double heterostructure laser. Okay, this is what is shown here. Is a double heterostructure laser because the well in the quantum well laser has a smaller dimension than, just stop there, just stop. This is basically what you also have in the quantum well laser, but in this particular structure that is shown in figure 23.19, the gallium arsenide thickness is maybe a few microns, and the thing extends, that is written as small d. The small d is a few microns or tens of microns, and so the current required is still large for lasing action. I repeat once again, these materials are transparent or nearly transparent to optical radiations. For example, gallium arsenide actually is transparent to radiation in the red wavelength range. So they are basically transparent materials. However, optical excitation is not a very efficient method of excitation, as we know from the principles of the Ruby laser. Electrical excitation is much more efficient, so excitation is made by passing current through the device. Now, if you again go back to the page where we have where they have shown the structure of a light emitting diode, just go back to that page, just under these pages. Okay. Yeah, move down, scroll down more. Yeah. Now here is the actual, stop here. Here is the actual line diagram of a quantum well laser. You see there are many layers, at least 5 layers you can see. At the top you have a metal deposition, and similarly at the bottom also you have a metal deposition. These are meant for electrical connection to the battery. Now under the top deposited metal connection, there is a layer of n-type gallium arsenide. Okay, and then underneath this you have a layer of n-type aluminium gallium arsenide, what was called gallium aluminium arsenide. So first you have this metal deposition, under this you have n-type gallium arsenide, then you have n-type aluminium gallium arsenide, and then you have a layer of p-type aluminium gallium arsenide, but in the middle you see p-type gallium arsenide. So if you look carefully, you will see that in the middle you have something like a cell phone type thing, a thin rectangular box, and that is the waveguide section of the crystal. It is in this that all the lasing action takes place. The rest of the thing is like a matchbox, uh, like a uh, box of matchsticks. But right within, at the center, you have a cell phone like uh, region, which is where the lasing action takes place. This cell phone like region is composed of P type gallium arsenide. So what happens is that if you look carefully, and then under that you have a region where you have p-type aluminium gallium arsenide, then underneath this you have p-type gallium arsenide, and then at the bottom you have deposited metal connection. So what happens is that there is a junction between n-type aluminium gallium arsenide and p-type gallium arsenide. If you look carefully, you will see that the layer just above p-type gallium arsenide is a layer of n-type aluminium gallium arsenide. So here is a p-n junction, and in this p-n junction, when recombinations take place, photons are emitted. These photons enter the cell phone shaped region, and because the cell phone shaped region has more refractive index than the rest of the matchbox type region, photons get trapped inside this region. They reflect repeatedly back into the region from the interfaces, and thereby the energy density of radiation within the cell phone type region increases, and stimulated emission can take place, and finally lasing action can take place. So that the laser light can come out, you can see that the end faces are polished flat. They have written both end faces of semiconductor are polished flat. That means the one that is shown and the one that is on the other side, they are polished flat, whereas the sides are not very well polished, so that the photons which actually cause stimulated emission are the photons which go back from one polished face to the other polished face on the other side. They basically move along or parallel to the horizontal plane that is that the cell phone type region essentially represents. It represents something like almost like a horizontal plane. The thickness is so small that it is almost like a horizontal plane, and in this horizontal plane all the stimulated emission and are produced, and they come out through the polished faces. They cannot come out through the side faces because the photons are moving back and forth between the polished faces. These are perfect, almost perfectly reflecting, so the photons go back and forth between the polished faces. Some photons get internally reflect from the interfaces, but some photons, because the side faces are not polished, they also escape into the aluminium gallium arsenide layers and get lost. So that is how the quantum well laser acts, and the lasers that we usually find in our labs, in our pointers and so on, are basically lasers of this type, the quantum well lasers. They are very efficient. Now, to get some more details regarding this, we have to move to the pages that I sent you yesterday. But before that, if we go back to the page that go back above the page that we had earlier regarding LED. Go up, go up. Previous page. Yeah. Okay, go up. Here, stop here. So you have this quantum well laser, where the well is in the shape of a cell phone. Okay, the size is mentioned in the diagram that I've just shown you, that comprises of 5 layers and then these metal depositions. The size of the end faces, the polished faces, is just 1 micron thick by 10 microns across. So it is very thin, very thin. 1 micron means just 10 minus 4 centimeters or 10 minus 3 millimeters. You see, it is so thin, it's almost like a line. So that is a very thin layer. Now, we consider quantum cascade layers. Now, in quantum cascade layers, they consist of hundreds of quantum wells. We saw just one quantum well. Now, if you have an electron of right energy, it can tunnel into the first set of quantum wells, drop down in energy level, and emit a photon. It says that if an electric field is applied across the device, the energy of each successive group of quantum wells. So you have in your device a succession of quantum wells. Okay, not just one quantum well, not one simple, one individual cell phone like region, a series of cell phone like regions, one under the other, and then another one under that. So if you apply a voltage from the top to the from the top was no, the top layer shown in that diagram was uh, of n type aluminium of n type gallium arsenide, and the bottom was p type gallium arsenide. So the voltage has to be applied from the bottom to the top. So p type has to be connected to the positive pole of the battery and n type to the negative pole. So if you apply such a voltage across a whole stack of such quantum wells, then the electron, as it moves from the top, because the electron moves in the direction opposite to the direction of the applied voltage, as the electron moves from one quantum well to the next quantum well, it gradually loses energy, and in each quantum well, as it recombines with holes, it loses some energy. So it progressively loses energy in a step-by-step fashion. And if you have 100 such wells, 100 photons will be emitted in the passage of one electron through this structure. If you move to the next page, you will see this. Move to the next page. Yeah. So if you have 100 such wells, one under the other, then another under that, and another under that, and so on, in each well, an electron will lose energy, and as electrons move, because recombination means while an electron is lost through recombination, another electron from the layer below that must start moving, because the electric current must keep moving. The electric current is conserved, the charge is conserved. So electron from the next layer moves and recombines in the next well, and then another electron starts from the next layer, and so on. So a continuous chain of such electrons keep moving from layer to layer, and in each quantum well, an electron loses energy and produces a photon. So if there are 100 such layers, 100 such photons would be produced, and therefore the total amount of radiation produced would be much higher. So you can see what is written in the next paragraph. Quantum cascade lasers can emit across the whole mid-infrared spectrum and into the infrared. The mid-infrared part of the electromagnetic spectrum between 2 and 20 micrometers is called the molecular fingerprint region, since many molecules, including pollutants, explosives, drug molecules, etc., and industrial chemicals and toxic gases absorb these wavelengths. In other words, if you send such radiation, infrared radiation produced by quantum cascade lasers through some uh, material which you suspect may contain some drug, or it may contain some um, pollutants or explosives, etc. Such materials will absorb the radiation, and by comparing the intensity of the radiation before you pass it through the suspected material, and after that you can see that absorption has taken place, and absorption takes place at specific wavelengths. So you immediately know which material is present in that suspected bag. So in this way you can immediately identify whether some contraband materials or some dangerous material is being transported or being kept hidden in a bag. So these are very, very important devices from the point of view of uh, applications. Also, I must mention that if you have heard of Fourier transform infrared spectroscopy, FTIR is again uh, a device which is used to identify the presence of certain uh, molecules or uh, molecular groups within a sample. So basically, FTIR can make use of quantum cascade lasers. So quantum cascade lasers are small devices, and they can easily be incorporated in a rather small apparatus, which can be used to identify the presence of certain molecules in a sample. So, uh, so FTIR is available at the Bosch Institute, and you can go to the Rajabajar campus and ask to have a look at it. So FTIR is a very, very powerful device which can be used to identify the presence of uh, different types of molecules in a sample. And this has been made use of even in whatever we did at the Bosch Institute regarding the structure of certain uh, nuclear track detectors. So FTIR is a device which is very useful, and it can make use of, or does make use of, the quantum cascade lasers, because you need a range of uh, infrared radiations and even visible radiations to scan across the uh, possible types of wavelengths that different materials absorb uh, when exposed to these things. So now we shall move to the material that I have sent you yesterday. We have basically covered the this semiconductor diodes and also the quantum well lasers. And now we can move to the material that I have sent you yesterday. So now here you get more details regarding the semiconductor diodes. This equation, the first equation that you see here, is nothing but how flux of uh, radiation of a particular wavelength or frequency nu changes as it passes through a medium. These things we have already studied in connection with the derivation of the Ladenburg equation. So we move to the next page. So you want to know whether radiation is absorbed uh, or stop here. You want to know whether uh, absorption is more or stimulated emission is more. They write RAB for absorption, RST for stimulated emission. So the rate difference is RAB minus RST into SdZ. So from the previous equation, you have d phi nu dz equal to a certain expression. Now you can identify that c square by 8 pi n0 square nu square tau r as the factor that we have encountered in connection with Leidenberg equation. Only there we wrote omega square instead of nu square. So you convert from omega square to nu square, the relation being nu equal to omega by 2 pi. So you can convert, and tau r is the mean life towards radiative decay. That is the spontaneous lifetime of the higher level that we have also seen. So on the right hand side, you also have phi nu, that is the flux of the incident radiation. And then you have a p nu factor, which is the density of states factor, which I have already mentioned. It is equal to twice mr whole to the power 3 by 2 divided by h cut square into h nu minus eg whole to the power half. This is the factor p nu. And then you have this difference of uh, this these f factors, which we already have encountered. These are the occupation probabilities. Uh, uh, these are the factors that were written as these are the factors which were equal to or written equal to f uh, f v ev into 1 minus f c ec and f c ec into 1 minus f v ev. So here again they have come back to the notation E2 and E1, right? I said that it is better to call EC equal to E1 and EV equal to sorry. I said that it is better to call E small v equal to E1 and E small v equal, sorry. I said that it is better to refer to E small c as E2 and E small v as E1. So whatever is written as E1 is the same as E small v previously, and E2 is E small c. So this FVE1 is the same as what we have referred to as FVEV into 1 minus FCEC, and FCE2 is the same as what we have previously called FCEC into 1 minus FVEV. So it's like that. So here you see, so this notation differences are okay. I'm rather sorry that you have all these notation differences, but then you are smart enough to see that which notation in one book is equivalent to another notation in another book. But the final thing that I draw your attention to is the same equation that we have discussed earlier, that if EFC minus EFV is more than E2 minus E1, then what will happen is that there would be more stimulated emission than absorption. On the other hand, if E2 minus E1 is more than EFC minus EFV, then there will be more absorption and less stimulated emission. So for lasing action, you require E2 minus E1 to be less than EFC minus EFV. This is the same condition as EC minus EV to be less than EFC minus EFV that we have encountered previously in another book. So now you have this absorption coefficient or the gain coefficient, because if the condition EFC minus EFV more than E2 minus E1 is satisfied, then you have gain. So gamma here is the gain coefficient. As written there, the gain coefficient is given by gamma nu equal to c square by 8 pi n0 square. N0 essentially is the refractive index. So so n0 square then you have a nu square, tau r, P nu, I have already mentioned what P nu is. It is the joint density of states. Then that expression, which we have already explained, that this is the same as Fc E2 into 1 minus Fv E1 in the uh, uh, pages that we have encountered earlier from another book. So now if you move to the next page, yeah, here they have, just a moment. Here they have written this expression in full. You see the gain coefficient written in expression in full, and that immediately tells you what P nu is. You can see that 2 mr to the 3 by 2 pi h cut square h nu minus Eg to the power half. That is P nu, the joint density of states. And the difference within the brackets is the same as this quantity. As you can easily see, if you write down the whole expression, that is, if you write down instead of FCE2, what was previously FC2 into 1 minus FVV, etc., you will find that this is the expression. So you have this expression for the gain. Now, if you go to the next page, here they have plotted the various things. So let us move to the next diagram. Just move to the next diagram. Here, just scroll down. Yeah, here. Just stop. So here they have written, they have computed the gain coefficient. The gain is per centimeter. That is what we previously called alpha. In the Loud's book, this quantity is referred to as alpha. And the gain over a length capital L is written as e to the power alpha v. So here that same quantity is denoted by the symbol gamma nu. So gain is plotted along the y-axis, and along the x-axis is plotted the value of this must be h nu. I cannot see. I have to really expand this. So this quantity must be h nu. So they plot gain against h nu. I think while taking the photograph, I have somehow missed the lower portion. But what is written here? Variation of gain coefficient. Here. H cut omega 0, that is h nu. So that is it. So you see that the gain as a function of the energy of the photon varies in a very interesting way. If the what is written beside the various curves is the number density of electrons in the conduction band. If the number density is as low as 1.5 into 10 to the power 18, you see that gain is negative. Gain is negative means there is absorption. So stimulated emission is dominated by absorption. But as the number of electrons per unit volume increases, you see that gain becomes positive, at least over a certain range of frequencies or energies. So it is positive, and the more the number density of electrons, the more positive it becomes. In fact, it crosses 120 for a certain energy, around 1.46 electron volt. So the gain is huge. Okay. So to produce stimulated, or rather to produce lasing action, we know that stimulated emission has to dominate over absorption, and therefore what you require is a high concentration of conduction band electrons within the active layer. So how can you produce a high concentration of electrons? Remember that electrons are injected into the active region by the battery. the battery injects electrons into the active region. So you have to inject more current. The more the current that you pass through the diode, the more it tends towards becoming a laser. And finally, if the number density of electrons, which is due to the injected current, or the concentration of injected carriers exceeds a certain value, you have lasing action or gain of the incident radiation. Where is the incident radiation? The incident radiation is just the photons which are emitted spontaneously. That is the initial step. Once you have some photons within the active region, then provided this condition that the concentration of uh, conduction band electrons is above a certain value, you can have amplification. However, as I said, these semiconductor lasers are not activated by shining light on them. So where does the initiating radiation come from? It is just by spontaneous emission. Okay, so let us move to the next page. Okay, so just let me make it. Yeah. So here they are calculating the electron and hole populations and quasi-Fermi levels. So we have noticed that lasing action takes place if EFC minus E. We have noticed that lasing action takes place if EFC, which means EF is the Fermi level, C stands for conduction band. If the quasi-Fermi level in the conduction band has an energy EFC, and the quasi-Fermi level in the valence band has energy EFV, then provided the difference of EFC and EFV is more than E2 minus E1, E2 is the energy of the electron before it jumps, E1 is the energy of the electron after it jumps, then lasing action takes place. So you have to relate the concentration of electrons with the location of the Fermi level. How to calculate that are given in these equations. 13.50, and then you have another equation for NV. Just move down, scroll down. 13.50 tells you how to calculate the concentration of conduction band electrons, and then you have a similar equation for NV, the concentration of holes in the valence band, because electrons have to drop into the valence band, and if the valence band has vacancies, then only such transition can take place. So you need to know how many holes are there or vacancies are there. So vacancy is what? The probability of a vacancy is 1 minus F V E 1. So 1 minus FV1 is the probability that there is a vacancy in the valence band at energy E1. So that way they calculate the concentration of holes in the valence band. So these are related to EFC and EFV. So if you know NC and NV, then you can calculate EFC and EFV, and then you can determine the range of energies, that is E2 minus E1, over which lasing action can take place. So let us move lower down to the next page. So yeah, move downwards. Yeah, here they are showing the energy level diagrams. So let us move down. We have already covered that. Okay, we have already covered this from another book. So let us move down. Move down here. Stop. Okay. Now, so what kind of current do you need? You see, to have a certain concentration of electrons or holes, you need to inject a certain value of current in the structure. Now, for steady operation, the number of electrons supplied by the battery per second must equal the number of electrons that are lost via recombination. And recombination results in the production of a photon. Now, these recombinations can be spontaneous or can be stimulated, but that is a separate thing. You have to have this equality of number of carriers injected and the number of carriers that get lost via recombination. One more thing I must point out at this moment. Note that the biasing has resulted in the production of a non-equilibrium condition. That is signified by the difference in the Fermi level in the conduction band and the Fermi level in the valence band. The difference EFC and EFV comes in because the system is not in thermal equilibrium. This is one of the conditions, remember, for lasing action. We have noticed this earlier, that if a system is in thermal equilibrium, population inversion cannot happen, and therefore lasing action cannot happen. So by applying a bias across the diode or the structure, you are actually producing a non-equilibrium condition. That must also be remembered. Lasing action takes place only under non-equilibrium condition. Now, coming to equation 13.56, you see that this quantity RSP denotes the rate at which recombination is taking place. So RSP is equal to delta N into AD divided by tau R. What is delta N? Delta N is the excess population of electrons over the equilibrium value. So if you have excess electrons over the equilibrium value, then you have a positive value of delta N. But these excess electrons, they soon recombine with holes and get lost. So the rate of recombination is given by delta N into A into D. What is A? A is the area of the interface between, let us say for a quantum well laser, it is the area of the interface between the gallium arsenide layer and the aluminium gallium arsenide layer. So that is A. And D is the thickness of the central gallium arsenide layer. This thickness is, as I said, of the order of 1 micron only. Okay. Whereas for ordinary or non-quantum well type lasers, this thickness can be say 10 microns or even more. Now, as you can see from this expression, the equilibrium, that is when you have the recombination rate equated by the rate at which carriers are injected, is achieved when the number of carriers injected per second across the junction is also equal to delta N into so this J actually stands for current density. So that means you have the current per unit area. The current per unit area is to be equal to delta N into E into D by tau R, because current per unit area is obtained by dividing RSP by A. So if you divide RSP by A, you get the recombination rate under unit area, and therefore the current density, that is the number of carriers injected per unit area, has to equal that. That is delta N into ED by tau R. So from that, you can, after putting appropriate values of the various quantities, a value of around say 808 amperes per, this A is not area, this A is amperes per square centimeter. So this is the threshold value, which means that at this value, the number of carriers that arrive newly within the structure equals the number of carriers lost via spontaneous transitions. If you pass a current which is larger than this, then you can have uh, more recombinations and stimulated emissions. So for stimulated emissions to dominate over spontaneous emissions, whose rate is given by RSP, if you want stimulated emissions to dominate over spontaneous emissions, you must pass more current per unit area than given here as J threshold. So that is the requirement. If you move downwards, scroll down. So here is, okay, the expression for the gain, and the gain is given by this expression alpha, I can't see, it is too small. Yeah, it is alpha into delta n by delta nr minus 1. So when the uh, energy, when, just don't scroll down, leave it there. So delta nr is the excess population of electrons per unit volume over the equilibrium value at the point where the rate at which the injected carriers equals the rate at which they are lost via spontaneous recombinations. So if delta n is more than delta n tr, tr is standing for threshold, then there can be gain. If delta n equals delta nr, then you have 1 and minus 1, so the difference is 0, and so there is no gain. This is the so-called saturation condition. So there is neither gain nor loss. If on the other hand the bracketed quantity is negative, the gain is negative, which means radiation, if allowed to fall in the active region, will actually get absorbed rather than getting amplified. So you have all these expressions. Just scroll down, you can scroll down. These are just other ways of writing this. Scroll down. This we have already encountered in connection with the derivation of the Swallow-Townes equation. This relation we have encountered. Actually, we had only minus 1 by 2L log R1 R2. But as I said, if there are other reasons for loss of photons, for example, scattering, etc., then you have to add additional loss factors, and here alpha stands for such additional loss factors. So let us scroll down, scroll down, scroll down. Yeah, scroll down. Yeah. Heterostructure lasers. This means that the device consists of materials of different kinds. In homostructure lasers, the basic material is the same, but one part is doped with p-type impurity, another part is doped with n-type impurity. For example, if the basic material is, say, gallium arsenide phosphide, then you can dope gallium arsenide phosphide with, say, tellurium to make it n-type, and dope it with zinc to make it p-type. So in case of such compound semiconductors like gallium arsenide phosphide, the doping has to be either by an element of group 2 like zinc to make it p-type, or by an element of group 6 which is of the n-type. So that is for a homostructure diode where the basic material is the same. like in silicon diodes, germanium diodes. These are homostructure diodes because the basic material is the same. But in heterostructure diodes or lasers, you have two different materials like aluminium gallium arsenide and gallium arsenide. These are basically different materials. Aluminium gallium arsenide is different from gallium arsenide. So in heterostructure lasers, you have at least two different types of materials. Okay. So if I move downwards, if I scroll down, here they have given the values of band gap as a function of the relative proportion of aluminium in aluminium gallium arsenide. If you write the composition as ALX GA 1 minus X S, then the band gap depends on X in that sort of fashion. If X is 0, that is, there is no aluminium, then the band gap is 1.424. This is the band gap for pure gallium arsenide. On the other hand, if you have pure aluminium arsenide, then X is 1 and the band gap is something like 2. Something like 2.7 or so. So the band gap can be varied widely. By changing X, you can vary the band gap from 1.424 to something like 1 from 1.424 to roughly 2.7 eV. That's a huge range of variation. And so if you change X, the shift in the position of the uh, energies, shift in the position of the bottom of the conduction band and the top of the valence band will be as given in these formulas 13.62. The the top of the valence band uh, goes down and the top of the conduction band goes up. So the separation between the bottom of the conduction band and the top of the valence band increases as you increase X, as you can see from formula 13.61. As you increase X, the gap increases because the bottom of the conduction band rises, the top of the valence band gets down lower. So here they have shown the structure of this heterostructure laser that we have already discussed. We have shown a detailed diagram of such a quantum well laser where you had 5 layers with the central one having a portion in the shape of a cell phone, and that is the region which actually produces the laser radiation. So that we have seen in much more details in a previous diagram. I think this is the last page, right? Yeah, I think this is the last page. So
Yes, sir.
yeah. So we stop here because we have more or less covered the necessary materials. If you go through these materials carefully, you will find all the uh, basically most of the required um quantities given there, except for the formula for joint density of states, which if you want, I can send you notes or uh, copies of pages where this is derived. But for the time being, I will not be doing that. And so, thank you very much for your huge patience because I have sent you materials from 3 different books with somewhat different notations. But then I thought it more helpful or more physically meaningful than what is given in Lord's book. So thank you very much for your patience.
Thank you, sir.
We shall have just one more class next week, and that will be the end of it. Okay. Thank you.
Thank you, sir.